Good morning, students. So we solved many problems based on the Gauss law and its applications. And so now finally we are almost at the end of that Gauss law topic, and which is ending, but it is very important to solve the many problems. These topics are very important to solve many problems in electrostatics. And that is, that means today we discuss about these properties of conductors. Properties of conductors. And first of all, we know about these conductors. What are conductors? And we discussed already about that. Basing on electrical properties, the materials are divided into three types. So one group is conductors, and other is insulators, and the third one is semiconductors, right? So now the conductors means it contains many charge carriers. That means more number of free electrons are available in this. And most of the metals are good conductors. So we are going to discuss about the properties of such a metals. And about the remaining classification. Insulators means insulators are nothing but which does not contain free electrons, or those are not suitable for the electric current to flow through it. And semiconductors means all the electrical properties lies in between conductors and say insulators. So then those are called semiconductors. And so now let us see about these properties of these conductors here. And now in this, the first point I can say that about this electric field. Electric field inside conductor is 0. The electric field inside the conductor is 0. That means, for example, how to conclude that means, for example, I am taking a metal here. Let us take it as an iron slab, iron metal. Now, suppose if I am assuming any electric field is existing inside. Suppose say I am taking that there exists some electric field in this region here. Like suppose the electric field is from left to right, right? Now, if we consider these electrons present in that, and we know as it is a conductor, it consists of a large number of free electrons. And so now all those electrons will experience a force because of this electric field, right? Because whenever a charged particle is present in electric field, there will be some force acting on this. And since it is a negatively charged particle, then this electron will experience a force like this. Not only that electron, whatever the electrons are there in this, such all electrons will experience a force like that. That means now all the electrons present in that material are traveling in this one direction. That means they are accelerating in one direction. And then we can conclude that some current is flowing in this conductor here. Because there is some net charge is flowing from one end to the other end, right? So that is nothing but that flow of charges is nothing but we call electric current. And so then you can conclude that some electric current is flowing through that conductor. In the absence of any external source, that you should observe here. Just you are taking an iron block, and if any field exists inside the iron block, then what will happen? That we are discussing here. So if any electric field exists inside this metal or inside these conductors, the electrons, the free electrons present inside the material should experience a force opposite to that of electric field, and so all the electrons will move in that opposite direction here, opposite to that of electric field, right? And so then there should be some net current flowing in that conductor. That means just if you are taking an iron rod, there must be some current inside this iron rod without applying any external source. External source means like a battery or any external electrical connections. Just if you are taking an iron rod, some current should flow through that iron rod. Is it possible practically? So no current will flow through that conductors, right? And so that from that you can conclude that the electric field inside the conductor must be 0. There should not be any electric field inside the conductor. So if electric field exists, this should happen. If electric field exists inside the conductor, then all the electrons present in the conductor should displace, or they should accelerate opposite the direction of this electric field. And so which is practically not possible. Practically there is no net current flowing through this conductor here. And so that you can conclude that electric field inside the conductor must be 0, right? So electric field inside the conductor is 0. That means you can conclude it must be 0 here actually. It must be 0 in the sense there you should remember in electrostatics. And later in the next topic we discuss about current electricity. Whenever current is flowing, then there exists some net electric field there because electrons will accelerate here. That means here no current is flowing in this conductor here. When no current is flowing, then electric field inside the conductor will be 0. And so that is a important point here. Electric field inside the conductor is 0. Right? Got it? Why it is 0 means this is the explanation. If any electric field exists, there must be some current flowing through the conductor in the absence of any external source. That means without even giving any battery connections or any other connections, some current is flowing through the conductor, which is practically not possible. And so that we can conclude that electric field inside the conductor is 0, right? And next. So then with this point and by applying the Gauss law, we can say many properties of these conductors here. By remembering this point, electric field inside the conductor is 0. And then with the help of this Gauss law, we can discuss so many applications there. That means so many properties of these conductors here. And next point, let us see. And while discussing about the properties of the charges, in the beginning of this electrostatic, there we discussed one property there. That property is nothing but any excess charge given to the conductor. So if you are giving any excess charge to the conductor, where it will reside? It will reside only on the outer surface. Like suppose if you are taking a spherical shell and if you are giving any charge to this spherical shell, this will reside only on its outer surface. That means we represent like this. If it is a conductor, if it is insulator, the charge may be present inside also. We are discussing about the conductors. So that means any excess charge given to the conductor will reside only on its outer surface. Now there I said we can prove this after discussing the Gauss law. Now I will prove that. That means now I am taking a spherical shell here. Spherical, that means it is a metallic. All we are discussing about the properties of metals only, that means conductors only. This is a thin spherical shell, and so that thickness is very small. This is the thickness of this spherical shell, that is very small here. Let's suppose R be the radius of this spherical shell, right? Now we are giving some charge to this. We are giving, it may be spherical shell or you may consider it as a solid sphere, anything you can consider here. Even you may consider it as a solid sphere also, no problem. Yes, I am taking it as a spherical shell. You may consider it as a solid sphere or any object you may consider there. Now, I am giving some charge Q, right? And so if you are giving some charge to this, that means we are giving by using some external agent, we are supplying some charge to this Q to this material here. Now to say where the charge is distributing, I am taking I am going to apply the Gauss law for this. So for this I am taking a Gaussian surface like this. So this dotted line is a Gaussian surface here. So this will be the Gaussian surface. So now just apply the Gauss law for this. So then integral of, that means flux phi is equal to integral of E bar dot ds bar is equal to 1 by epsilon naught times q in, right? That is our Gauss law. And so now our Gaussian surface is, where we are assuming the Gaussian surface means just inside the boundary of this material, right? That is the Gaussian surface where what we are assuming here. You may consider it as a solid sphere or any spherical shell or any irregular shape also you may consider there. No problem with that. But whatever the irregular shape you are taking, suppose if you are taking an irregular shape like this is a conducting material, for example, if I consider, and for this, for example, if you are giving some charge to Q here, just we need to consider a Gaussian surface just inside the surface of this material here, just inside the boundary. So that will be the Gaussian surface here. So for this, any object you may consider, any metallic object you may consider there. So just we are taking the Gaussian surface just inside the surface. And now if you apply the Gauss law here, so by using this first point, our first point is electric field inside the conductor is 0. And so now we are taking a Gaussian surface inside the conductor only, just inside the conductor only. And from that you can conclude that electric field is 0, right? So So that means this is inside conductor, electric field is 0. That is E is equal to 0. Means I will write here that is E is equal to 0. That means in this expression that E is equal to 0. If E is equal to 0, then you can write that therefore you can write this flux is equal to 0, which is equal to 1 by epsilon naught times the charge enclosed, right? And so from that you can conclude that charge enclosed is 0. Charge enclosed is 0 means where we are taking the Gaussian surface we are taking the just below the boundary of this object or just below the surface. That means inside this Gaussian surface there is no charge. So inside this there is no charge means where the charge should be. So the excess charge given to this material should be distributed only on its outer surface. And so that charge will distribute only here. Only on its outer surface, outside this Gaussian surface. So outside the Gaussian surface means only on its outer surface you can conclude there. So that is that point here. So that is a proof for this. So for any object, just we need to consider a Gaussian surface inside this material, just inside the boundary, and from that you can conclude that point here. All these points are very simple points, you can understand them easily, but they are very important points here. So just write that second point there. The excess charge given to the conductor, resides only on its outer surface. Which can be proved by using Gauss law as follows. Then you can copy that. And see the next point. Next here, if you are considering that any object is in the while we are discussing about this say electric field lines, properties of electric field lines, there also we discussed one point, right? That point is nothing but one of the properties. There we discussed actually one previous IIT question also. I think all of you remember that. That means if this conducting sphere is placed in some electric field, then how the electric field lines will be. So then we discussed a problem like this. Right? So if electric field line, suppose say ABCD or given like this, then which of that line, electric field line, will represent the correct representation of the electric field. And so there we discussed that just 2 points there. Inside the conductor, no electric field line should exist because electric field inside the conductor is 0. Just now we discussed that electric field inside the conductor is 0 because electric field lines itself, they are used to represent the electric field. If no field is there means no electric line of force should be there. And no line should exist inside this material. So clearly you can say that B and C are wrong. And the next point is the field lines should start or end on the surface normal to the surface, right? And so that means now this A is not starting or ending on the surface here. They are like this. These lines are straight lines only. So they are not ending or starting normal to the surface. So here these lines are ending or normal to the that means starting or ending on normal to the surface. This line is ending normal because this line will extend if it passes through the center, and this line also starts here because when you extend this, it is passing through the center. That is the meaning of the dotted line there. It is starting in the direction there. And so now that is the representation here. Now you can prove this about this point here. Why it is normal to the surface. So that is our third point now, or third property we can discuss now. So that means if any electric field is starting or ending on the surface, it must be perpendicular. Like suppose again I am taking a block here. If suppose electric field I am taking that on the surface, electric field is making certain angle here, right? Electric field is making certain angle on that surface. We are assuming that it is placed in some external field. This total block is solid block is metallic block is placed in external field, So the electric field is like this, making certain angle theta with this surface of this material. That means we are taking that the electric field is not normal to the surface. And now let us see, let us resolve this into components here. This is E cos theta and this component will be E sin theta, right? And so, now say this. Now E cos theta component is there here. That E cos theta is component is there tangential to the surface. Now again you can come back to our first property there. Now that means there exists some electric field parallel to the surface, on the surface. And so that means it is a metallic, and as it is a metallic, it consists of many free electrons here. And so those electrons now again accelerate in this direction here. They will experience a force in the direction, and so that they will accelerate in that direction, right? And so because of that, again there must be some current flowing in that conductor there without applying any external connections, without any external source, so which is again practically impossible. That means this component should not be there. E cos theta component should not be there. If E cos theta component, that means if any tangential component exists, because of the tangential component, the electrons present in that material should accelerate opposite to that. And so then because of that, there must be some current flowing through the conductor without any external source, so which is practically not possible. And because of that reason, this component should not be present. And so that you can conclude that this E cos theta value should be equal to 0, right? So E cos theta value is 0 means I can say that cos theta value is equal to 0, because E value some finite field will exist there. And so now it is theta value is nothing but you can say 90 degrees, and therefore this field must be perpendicular to the surface of this conductor only. That field must be like this only. If any field exists, that field must be like that only. So that is the conclusion there. So electric field at any point on the surface must be always perpendicular to the surface. So write that as the third point. Electric field at any point on the surface of a conductor, the electric field at any point on the surface of a conductor is always normal to the conductor, is always normal to the conductor. And if you want explanation, then you can write about this. I think that explanation is not required. If you want explanation, then you can write this explanation here. Right? Consider the explanation for that. Consider the electric field is making an angle theta with the surface of a conductor. The electric field is making an angle theta with the surface of conductor. Then the component E cos theta will be parallel to the surface. Then the component E cos theta is parallel to the surface, and E sin theta is perpendicular to the surface. E sin theta is perpendicular to the surface. So due to E cos theta component, the electrons present, the free electrons present in the material, should accelerate opposite to it, due to which some current should flow in that material without any source. Some current should flow in the material without any source, which is practically impossible. Therefore, E cos theta value should be E cos theta is equal to 0. From that, cos theta is 0. Therefore, this theta is equal to 90 degrees. Theta is equal to 90 degrees. Theta is 90 degrees. That is, electric field must be perpendicular to the surface. Now here you may get some question, that is we are discussing about only E cos theta. Then what happens due to that E sin theta component, or what happens if the electric field is normal to the surface? So then why the electrons are not displaced due to this component? Electrons will displace due to that component also, and because of that reason only opposite charges will appear on that surface there. On one side you will get the positive charge, on the other side you will get the negative charge. Effect will be there due to this perpendicular. That means here what about this component E sin theta is there. Actually finally we are concluding electric field is normal to the surface. So because of that reason only charges will appear on the opposite surfaces there. We will discuss that now. And previously in the second point we discussed that the excess charge given to the conductor will reside only on its outer surface, right? That you can also discuss by using our Gauss line differential form. If you understand it, that's okay. Then you can also explain by using this differential form, Gauss line differential form. So Gauss line differential form we can write like this: del bar dot E bar is equal to 1 by epsilon naught times the charge enclosed. The second point, again I am explaining the second point by using another way here. So then here inside this value is 0. This value is 0 means then this from this, that means E value is 0 inside the conductor. That implies you can conclude that rho is 0. Rho is 0 means no charge will be present inside the conductor, or the charge density inside the conductor will be 0. The charge density inside the conductor means that charge density is nothing but excess charge. It doesn't mean that no electrons are present in that region. Electrons will be there and protons will be there, so that their net charge will be 0. Whatever the excess charge you are giving to that conductor, that excess charge will reside only on the outer surface. There is no excess charge inside this Gaussian surface. So that is, we can also explain by basing on this also, the point. And based on this only now we can explain that. So write that next point. As the electric field is always normal to the surface of a conductor, as the electric field is always normal to the surface of a conductor, if a conductor is placed in external electric field, if a conductor is placed in external uniform electric field, external uniform electric field, then there will be some distortion, or there will be some disturbance produced in the electric field due to this conductor, due to the presence of the conductor. That is, the electric field lines will end on the surface normally on one side, and they will start normally on the other side of the conductor, as shown in figure. That means now whenever you are placing an external, that means a conductor in external field, initially the field will be uniform. So initially the field is actually like this. Initially uniform field means we need to represent that by equidistant and parallel lines. Now once if we place such a conductor inside this, then there will be some disturbance or distortion produced in that. So that distortion is nothing but because of this property here. The electric field lines start or end normal to the surface of the conductor, right? And next point. So this will be fifth point. So it means here itself we can say that It is nothing but you can say that here, for example, if you are taking it as a spherical shell here, if you are taking it as a spherical shell, we know that the electric field inside this conductor will be 0. Or you can say that, for example, I am taking a some conductor like this. Now I am taking some conductor like this, or you may take any shape here. And so now these lines will be the electric field lines, or suppose say like this. The electric field lines or ending or starting like this. Right? So now the electric fields, or suppose say electric field lines or like this, when it is placed in some uniform electric field here, then what I can say is here inside this net electric field will be 0. And so that is nothing but some charges will be induced on this. I think you can understand that easily if I am taking a plain conductor like this. Let us take it as a plain, like a plain conductor like this. Now some electric field is, it is placed in some uniform electric field like this. And so now here the electric field lines will start or end normal to the surface like this. Now here the thing is, the electric field inside the conductor will be 0. This we already discussed there when we were discussing electric field due to the plane of conductor. Now here electric field is 0 inside this, means the resultant electric field is 0, right? The electric field due to the external, this is the external electric field here. There is some external electric field is there along this direction. I will explain. So then this is our, when you are placing an external field like this. Now here there will be two types of electric field. That means here resultant electric field is 0, net field is 0 in the sense. So that means resultant field is nothing but one electric field will be there like this, which is external. External electric field will be there like this. Because of this external electric field, some induced electric field will be produced in this. Induced electric field is nothing but because of the charge separation. When a conductor is placed in external electric field, now as I said in the previous, like sin theta, d sin theta and d cos theta component, here electric field is normal to the surface. Normal to the surface means, if suppose if I consider some electron is present here, now the electric field is along this direction initially when you are just placing this material, then because of that these electrons will come opposite, that means they accelerate opposite to that. And so then negative charge will appear on the surface here. Negative charge will appear on the surface, and here positive charge. This will be, that means all the free electrons will accelerate towards this, and so here excess negative charge will be there, and so this side this positive charge will be there here. So that is actually the reason why we discussed, that means we discussed already at the induced charges. That means when beginning of this in the first class we discussed like charge can be produced by three methods, like friction, rubbing, or by conduction and by induction. So this is nothing but the induction. That is why when this positively charged plate is placed near a neutral plate, when the positively charged plate is placed, positively charged plate means we know it is they are closely placed here, so that you can take this this plate as infinite plate. When compared to this distance, the size is very large. Infinite plane means it produces a uniform electric field like this only. Uniform electric field is produced by this plane sigma by 2 epsilon naught, which we already discussed. And so now this plate is placed in such electric field here. And so because of that electric field, the electrons will separate, or electrons will displace to one side. That means opposite to that of electric field. And so this electric field will be acting like this. Now the electrons will accelerate like this. And so that positive charge will be induced on the, negative charge will be induced on one side, and a positive charge will be induced on the other side, such that net charge on the conductor is 0, same as that of this induced charge here, right? So that is why the induction will take place. When you are placing a neutral charge near a charged object, neutral body, neutral metal plate near a charged object, the induction will take place because of this electric field here. The induced charges will appear on the surface such that the resultant electric field inside the conductor is 0. So that is the main thing to be happen there. inside this conductor net electric field should be 0 on at any point. So this, now you can observe this external electric field is along this direction from left to right. Induced electric field is from positive to negative charge, it is towards left here. So they cancel with each other, and so I can write here the net electric field is external electric field plus induced electric field. This value should be equal to 0. Therefore, I can write this induced electric field is equal to negative of external electric field. That means it produces exactly the same amount as that of the external electric field. The negative sign is they are opposite each other, just their directions are opposite each other here. They are equal in magnitude and opposite in direction, so that the resultant electric field will be 0. So next mention this point there. I think it's the 5th point. When a conductor is placed in external electric field, then induced charges will appear on its surfaces. Induced charges appear on the surfaces as shown in the figure, such that the electric field due to the induced charge, is cancelled with the external field. So that net electric field inside the conductor is 0. So the next point in this. So then you can draw this diagram and write that equation there. So this is true for the conductor only. You should also remember that we are discussing only the properties of conductor. If you are taking it as a non-conductor, then you can't write this relation here. This induced and these two are equal in magnitude. This is a vector here. I can write here their magnitudes are equal. So magnitude of this induced field is equal to magnitude of this external field here. They are equal in magnitude and opposite in direction there. And now let us say this next point. Electric field near the surface of a charged conductor. That means we need to calculate external electric field due to the charged conductor very close to its surface here, right? That means now here you may consider the conductor of any shape. So consider the conductor of any shape here. Suppose I am taking a conductor of this shape. So it is having some positive charge density sigma, surface charge density sigma here. So consider this is a conductor of any shape. So just mention that consider a conductor of any irregular shape having surface charge density sigma. So that means now we are going to derive an expression for electric field due to this conductor. For regular objects we derived already. Now this is an object of conductor of any shape. So we need to derive an expression for electric field due to the conductor of this any shape here, right? So for this I am taking this small elemental area here. So this area I am taking here. So then with that area let us take a Gaussian surface. Right? Let's suppose that area be dA, let us take here. The area of this surface, this area is dA I am taking here. So then with the area dA, we are taking such a cylindrical surface. Now this is our Gaussian surface. So that cylindrical surface is nothing but our Gaussian surface. We need to find electric field at this point here, right? So now we need to write the electric field at this point here. This is suppose a point A, and this inside this I am taking this as a point B here. And so now here the direction of electric field at this point will be away from this positive charge. We are close to the conductor, so electric field will be away from this positive charge here. So this will be along this direction. And area vector dA bar is also along the same direction here. But inside this, at the point B, if you consider, then electric field inside the conductor is 0. That means here there is no flux passing here. Here electric field inside the conductor, so electric field inside the conductor will be 0. And as the electric field is for the remaining curved surface, that means we discussed about the plane surfaces. There will be some flux passing through the top surface because these two are parallel, and flux passing through the lower plane surface will be 0 because electric field is not present in that region here because it is inside the conductor. Inside the conductor is electric field should be 0. So that is the reason here, no flux is there. Next we should discuss about this curved surface here. The electric field, electric flux passing through the curved surface. So if you are taking here, electric field it will be along this direction and area vector will be along this direction here. So for this curved surface, electric field is tangential to the surface and area vector will be perpendicular to the surface. So flux passing through the curved surface is 0. That means I am writing like by Gauss law. So by Gauss law we can write it as flux is equal to integral of E bar dot ds bar or dA bar, which is equal to 1 by epsilon naught times the charge enclosure Q in, right? And so now this flux we can write as flux passing through the curved surface E bar dot dA bar, that means due to the surface A, top surface, and flux passing through the bottom surface B, and flux passing through the curved surface. This is equal to 1 by epsilon naught times the charge enclosure, right? And so now the for this surface we can write E into dA into cos 0. This is for the surface A. For this E is 0, and so that this value will be 0. And for this E into dA into cos 90 for the curved surface. This is equal to 1 by epsilon naught times charge enclosure we need to write here. Can you say how much charge is present inside this Gaussian surface? That is nothing but charge present in this area dA here. So charge present on that surface dA we can write as sigma into dA, right? Charge into, that means charge density into area. That is the charge enclosure there. And so now this value you can simplify it as so this is nothing but here I think this we are writing flux for the small element only, then this integration symbol is not required here. Flux through the small element only we are writing here, then this integration symbols are not required. So directly you can write that E into dA. Because if you are taking integration, then integration should take that side also, then total charge we need to write here. By using by Gauss law for small element. We are applying for this for the small element only. D5 let us take this one. And now this value we can write this expression as E into dA is equal to. Now this term is 0, already B is 0, flux passing through the surface B is 0. This I will write like this is the flux through the surface A and flux through the surface B and flux through the surface C. So this is the flux through the surface A and flux through the surface B is 0 and this is the flux through the surface C. And so now this is E into dA is equal to 1 by epsilon naught times sigma into dA. Therefore, E is equal to sigma by epsilon naught you will get. So that will be the electric field due to the conductor of any shape. And you should consider that very close to the surface of the conductor. That means just outside the conductor only. This expression is not far from this conductor here. So it is the expression for electric field due to the conductor of any shape. So just write that the electric field due to the conductor of any The electric field due to the conductor, due to the charged conductor of any shape just near the surface, just outside the surface, or that means just very close to the surface, just very close to the surface is the electric field at any point. That means electric field due to the conductor of any shape just close to the surface of conductor sigma by epsilon naught, right? And so there when we are discussing about electric field due to the surface, electric field due to the spherical shell or the solid sphere, there I mentioned one point there in that class. So that means I said I wrote this expression there for the sphere and I mentioned that, remember that point. That means now let us prove for this sphere here. Suppose I am taking a spherical shell, for example, here having some charge Q, right? It is of radius, or let us take here. Now just I am taking just outside here. Just outside means almost on the surface I am taking. So let us write electric field due to the sphere just outside the surface. So then our formula is Q by 4 pi epsilon naught into R square, right? And so now this I can write as Q by 4 pi R square into epsilon naught. Now this Q by 4 pi R square is nothing but Q by A, charge per unit area. And so which is nothing but sigma by A, sigma by epsilon naught here. So this is the electric field just very close to the surface or on the surface of this conductor. That means spherical shell or a solid sphere here. So that is true. That means that is the proof for this. So that is true for any conductor. For any conductor, only the restriction you need to remember is just very close to the surface or just outside the surface of the conductor there. So that is the point here. So mention that point. Just outside the conductor of any shape, the electric field is given by that expression sigma by epsilon naught. So you can use that point for any conductor there. Any conductor, that means any shape. And some other properties will be there, like about the cavities and the charge present inside the cavities we need to discuss. And I will explain those properties in the next class, the remaining properties of these conductors in the next class. Okay, these are some properties which we are discussing there, and so the remaining important properties will be there, and those properties I will explain in the next class. Thank you.